Okay, let's continue into some messier examples of using L'Hopital's rule. So this first one, always check and make sure you've got your 0 over 0 or infinity over infinity form. When m approaches 1, and the reason we're only approaching from the right is because that natural log function would be undefined. Oh, actually it wouldn't be. I don't know why. There's probably a reason at some point in this where we would have a domain problem. So as m approaches 1, natural log of 1 is 0, so the top is getting really close to 0, and the bottom as well. 1 minus 1 is 0, which means this is a valid place to apply a L'Hopital's rule. We got to be a little careful because there's some chain rule stuff we're going to have to do when we take the derivative. So we have 7 times natural log of m squared. We want to first look at 7 times stuff squared. So the 2 is going to drop down and make it a 14 times stuff to the first power. So we get a 14 natural log of m. Do not forget that you have to multiply by the derivative of your stuff here. This looks funny to me. I'm going to give parentheses. So we do have to multiply by the derivative of natural log m. On the bottom, we have negative 5 times stuff squared, so it's going to become a negative 10 times stuff to the first, and then we would have to chain out a derivative of m minus 1, but the derivative of m minus 1 is 1, so I think we're actually set on that. And then we should investigate again. So here, as m approaches 1, we still have that natural log of 1 is 0 on the top, and we still have the 0 on the bottom. So we can go for it and we can just apply a L'Hopital's rule again. My advice would be to do a little simplification first, just because if nothing else, it makes the derivatives easier. So I'd like to fix the fractions in fractions. So at any point, not just in the first step, you can go ahead and use algebra to rewrite your fraction a little bit. So I'm going to be looking at 14 times the natural log of m over, and in fact, while I'm at it, since I'm going to take the derivative, I'm just going to distribute it in the negative 10m. So it ends up being a negative 10m squared, and then it's a positive 10 plus 10m. So both the m that I'm multiplying through and the negative 10 got run through in that step. Okay, and then we can check again, see if the algebra changed anything, but I don't think so. Right now, if we plug in 1, natural log of 1 is 0, so the top is 0, and on the bottom we get negative 10 plus 10, which is 0. Okay, so this is still a 0 over 0. As long as it stays indeterminate, you can just keep applying a L'Hopital's rule. So if you hit a point where it's not indeterminate, it's just straight up undefined, like you have a 1 over 0, then you're going to need to try looking at graphs or plugging in numbers or something. But this is not a definite undefined. This is just still indeterminate. So I'm going to apply L'Hopital's rule again. But remember, really check closely. If you're doing this and you don't actually have a 0 over 0 or infinity over infinity form, this is going to give you nonsense. Okay, so the derivative of 14 natural log m is 14 over m. And then on the bottom, negative 10m squared plus 10m is going to become negative 20m plus 10. And now, if I plug in 1, I get 14 on the top, and I get negative 10 on the bottom. Negative 20 plus 10 is negative 10. So I'm getting negative 7/5 as my answer. So it is completely valid to apply L'Hopital's rule more than once. Do be thoughtful about it if you're working on, I don't know, exponential or trig functions, whereas you keep applying, they're just going to kind of rotate back and be pretty much the same as what you started with. That might not be productive. But as long as you think you can make things simpler by taking another derivative, go for it. Check for that indeterminate form and go for it. I think I at least got one on your homework where you have to do it 3 times, maybe 4, so don't be shy about continuing to apply it. Okay, so there's one trickier thing about L'Hopital's rule. Another thing is this one is not actually in a 0 over 0 or infinity over infinity form. Right now, as k approaches 0, this is getting really, really big. And sine of 0 is really close to 0, so this is as well. Both of those were dividing by a tiny number. I think this one should probably have the plus. I never paid attention to why the last one did, but let's give it to this one, because otherwise I think that we could be getting weird things on either side. Okay, so when you have this, infinity minus infinity, I mentioned it before, what's really happening is we have a 1 over 0 minus a 1 over 0, and getting a common denominator and making it a single fraction can make it something that we can apply L'Hopital's rule to. So what I want to do is multiply the first fraction by sine k over sine k, and multiply the second fraction by k over k. And there's my common denominator, and when I mush this all together, I'm going to get sine k minus k over k sine k. As k approaches 0, so I haven't done any L'Hopital's rule so far, all I've done is some algebra. As k approaches 0, on the top, sine of 0 is 0. 0 minus 0 is still 0. So the top is going to 0. And then on the bottom, it's basically 0 times 0. Now I can apply a L'Hopital's rule. So if you get fraction minus fraction, infinity minus infinity, try getting a common denominator. Okay, so derivative of the top. Derivative of sine k is cosine k. The derivative of k is 1. On the bottom, we'll need a product rule. So second sine k times the derivative of first, which is 1. And then we're going to have first k times the derivative of sine k, which is cosine k. So the bottom maybe looks a little messier, but the top is getting simpler in some way. The k became a 1. And now when I plug in 0, I get cosine of 0, which is 1. 1 minus 1. So the top is still approaching 0. Let's see about the bottom. On the bottom, I have sine 0, which is 0. And then I have 0 cosine 0, which is 0 times 1, which is 0. So everything on the bottom is headed to 0 as well, which means I can apply a L'Hopital's rule again. And while this did get a little messier, I'm seeing that k is going to be gone by the time I do a second derivative. I'm still going to go for it. You can always try these, and if they're not helpful, you can backtrack. So derivative of cosine is minus sine. Derivative of 1 is 0. And then on the bottom, the derivative of sine is cosine. And then we have to do a product rule again. So we get cosine k times 1. And then we get k times minus sine k. Okay, so again, we're adding terms to the bottom, except the cosine k's add up to a single term. That's really a 2 cosine k that I have down there. So if you want to knock it down a little bit, you can. Okay, so now as k approaches 0, the top is still 0. Sine of 0 is 0. The bottom, cosine of 0 is 1. So I have a 2 minus 0, so the bottom is 2. So I'm getting a 0 over 2. And that is not indeterminate. If you take 0 and divide it by 2, you get 0. So it took us a couple of L'Hopital's rule, but we really did get to something that was no longer indeterminate. Okay, one more here. Oh, no, I lied, 2 more because they're tied together. So I've showed you that you can use L'Hopital's rule more than once. I've showed you that if you have infinity minus infinity, you can make a single fraction. Now I want to show you a little bit of that natural log trick, and then from here on out, it's just more examples and practice. Okay, so this first one already has the natural log, so not really much needed in the way of tricks. So let's look at what we've got. U is going to 0. The natural log of u, if you think about what natural log looks like, this is why it's so important to have these graphs in our head. As we approach 0, as we move toward the y-axis, the natural log goes to negative infinity. So this is an indeterminate form, really big number times a really tiny number, who wins, but it's not a L'Hopital's rule form. We need 0 over 0 or infinity over infinity. Okay, so here's the trick with these. We can rewrite, okay, so let me think of how I want to say this. This is a multiplication. You can always interchange multiplications with divisions, right? So division is the same as multiplying by the reciprocal. And here I just want to kind of go backwards. So say multiplication is the same as dividing by the reciprocal. So all I'm doing here is algebra. Well, this might sound tricky. Let me just write it down. I don't think you'll think it's too weird once I do. I'm going to say that multiplying by u is the same as dividing by 1 over u. And if you aren't initially convinced, try and reverse it. If I'm dividing by 1 over u, I would flip that. I'd get u over 1 and I'd multiply. And these are the same thing. So if you ever get a 0 times infinity, flip 1 and put it in the bottom. And now the natural log of 0, that's headed to negative infinity. And as u approaches 0, 1 over u is headed to positive infinity. This is a L'Hopital's rule form. We don't care about the minus sign at all, but that infinitely large over infinitely large is a valid one. So now I can say, according to L'Hopital's rule, the derivative of the top is a 1 over u. The derivative of the bottom is a negative 1 over u squared. Remember, 1 over u is u to the negative 1. So we get negative u to the negative 2. Which is still an infinity over infinity, infinity over negative infinity. But this one we can apply some algebra to. So I'm going to say, okay, well, let's flip and multiply. Kind of undoing what we did at the beginning. So we have a 1 over u times negative u squared over 1, and we can cancel a u out of that. And as u goes to 0, opposite of u also goes to 0. So we have a value. The limit approaches 0. Okay, so if you have 0 times infinity, get the reciprocal, divide by the reciprocal instead. See if you can make it infinity over infinity. Or we could have done this u over 1 over the natural log of u. And that would mean that the top was headed to 0. And then the bottom, the very, very bottom is headed to negative infinity. So 1 over that is also headed to 0. And that would have made it 0 over 0. The reason I went the way I did was it's a lot easier to take the derivative of 1 over u than it is to take the derivative of 1 over natural log u. But it's totally doable either way. So your pick. Okay, so new question. And this is really closely tied in. And our goal would be I'd just ask you question D and you'd know what to do. But I wanted to work my way up to it. So this is a 0 to the 0. And that's an interesting question. That's a weird one where you have a really tiny base raised to a really tiny power. Kind of funny things can happen there. Let's see, okay, so this is one of those, whenever you have an exponential form, you can introduce a natural log. So this is not going to find me the value of u to the u, but I can find the value as kind of a side problem of the natural log of u to the u. So just introduce a natural log, we'll get rid of it later. And the reason this is helpful is because logs have a really nice property where you bring the power down and now we have a product. So we had the natural log of 0 to the 0. Now we have our 0 times negative infinity that we had before. And we don't have to walk through the whole process. But again, remember that the idea would be if you have a 0 times infinity, flip one of them and put them in the bottom. It doesn't matter which one. And that makes it a negative infinity over infinity. It's a really ugly infinity. And then we'd work through the exact same steps as before, but rather than walk you all through that again, we'll do more examples later. I'm just going to say that from the last part, from C, we figured out that the value of that limit would be 0. the important thing here is to realize that what you just said was that the natural log of u to the u is approaching 0. But the question was, what is u to the u approaching? So you can think of this a couple of different ways. One is, what do you take the natural log of to get 0? The other is, if you kind of think of it as an equation, you can exponentiate. So if you took all that and put it up in a power and made e the base, it would cancel the natural log. And then if you did it to the other side, that would mean that's approaching e to the 0, which is 1. So we wanted to know, what is u to the u getting close to? And the answer is u to the u is getting really close to 1. Okay, so hopefully that gives you some ideas. I have more in the next example, but feel free to go try some more on the homework, some of the trickier ones, and then come back if you get stuck again.